Hey guys, welcome to this new tutorial in Unity. So let's see, this is going to be the third part of the building the game of life by Conaway, and this is where we left off. We had the grid with an randomized type for this prefab, these cubes, and also we had a debugging system that would allow us to, let's say, visualize with the text tag, some of the information of these elements, right? So let's, for now, just turn off this. I mean, we could basically, we mentioned this, we could actually do that into a function. This is the part of the code that had to do with basically visualizing that label. So we could call it function debug data. And we can just basically leave all this stuff here. So cut and paste, and for now we're gonna comment it out, right? So we actually don't get that information, right? So let's kind of spend some time really building the rules of the CA, which is mainly what we're gonna do, right? So this is a creation of the grid. That's good. And basically what we're missing here is just in this area on the CA calculation object, start dealing with the calculation, which is basically how does one unit in the grid calculates who is his neighbor to the left, basically all the 8 neighbors that a cube would have, right? So, and if you just wiki Game of Life, you'll see what are the rules. There's 4 rules, I believe, and we're gonna write them one by one. So yeah, this is 1, 2, 3, 4, 5, 6, 7, 8 neighbors for one entity, right? So basically we need to calculate all the rules of all the cubes. And that would actually make an emergent pattern, right? So basically we need to do this in a for loop, or in the in two-dimensional for loop, to basically go through each one of the grid elements, right? And change its state based on the number of neighbors that he has, right? So let's write some of the, I mean, the rules, I have them here actually, but you could just look at them in Wikipedia. There are 2 kinds of rules. Let's write some comments here. Rules. So 1, this is for alive cells. So for cells that are alive, right? And the second type of the second type are for the cells that are dead, right? So what determines that a cell is alive or dead? We're using the variable type, right? So 0 is going to be dead, 1 is going to be alive, right? So basically, and how do we access actually that information? We've done it here with this element. So what we're going to do is like grid X and Y. This represents the element in the grid that we want to evaluate, right? So that's the get component, and we need to get the component CA cube. And if we now basically we access this script here, right, with this, and then we can actually type .type, and that would be this is basically one cell or one of these cubes, and it's returning, this variable is returning the value of that type, right? So but this is the cell itself, right? So let's put this in a calculation. So this is for the cells that are alive. So if this equals 1, that's alive, something happens, right? And if this condition equals 0, something else happens, right? So we have rules of 2 kinds for we could indent this further, and there we go. Right, so far so good. Let's start by the we basically, what we need to do is, because all the rules have to do with the number of neighbors that each element has, we need to first count the neighbors, right? So let's create a variable for that. So variable neighbor count. That's for neighbor count. And we're gonna start with 0. This should be an int, just in case. And we have to evaluate each one of the neighbors of this grid, right? Just because now we have an index here, basically a position in the grid, we can actually ask something like if, similar to this, right? If that condition, but here we could actually ask the -1, right? So x represents the location in the grid, but if we ask -1 here, we could actually ask for the neighbor to the left, right? And we could say, then we're gonna do just a one-line if statement. Count, our variable gets a ++, right? So basically this line is saying if my neighbor to the left is alive, right, it's 1, I get a ++. So I'm counting how many neighbors do I have, and I basically have to do that for every cell, right? So if you imagine you are any cell in the grid, your neighbor to the right would be +1, right? I'm gonna write a few of them here. So your neighbor down and your neighbor up, right? So that's 4, and we need 4 more, which are the diagonals. So -1 and -1, +1 and +1, +1 and -1, and -1 and +1, right? So what we're doing here is just like going through each one of the cells around me and checking if I have any neighbors. And this variable will start from 0 every time, and it will add up to a maximum of 8, and I could actually take some decision based on that, right? The problem of this part of the script, this part here, is that if you're in the borders of the grid, you're gonna have an error. Basically, you're gonna get an error saying, well, I don't have a neighbor to the left. You know, if you're on the left side. If you are in the top bit, you're gonna say, I don't have a neighbor up, and every so for all the border of this kind of grid. So we have to just basically, before this, do an if statement saying if x is bigger than 0, right, and x is smaller than columns -1, which is in this case 19, right? So it has to be smaller than 19. 19 is the last one. As we start from 0 to 20, I mean 19 would be the last one, really. And I is smaller than 0, or it's bigger than 0, and I is smaller than rows -1, right? So this if statement that should go all the way down here, right? Again, if you want to just maybe all of this part indent like that, so we can make sure that our curly brackets are being closed properly. This calculation should only happen if you're not one of these borders, right? So let's check that that's actually working and we're not running into any errors so far. So yeah, we're not getting any errors, you can see. So it seems that it's fine. That's good. And the next step would be really writing the rules, right? So the fourth rule, which is the one that I'm going to really start with, it's quite simple, which is for the cells that are alive, right? So sorry, for all the dead cells, which is this one, right? If a cell is 0, there's only one condition in which a cell gets born out of that, which is if it has exactly 3 neighbors. So if neighbor count equals 3, right? So exactly 3. We're gonna say that the type grid.xy get component type equals 0, sorry, equals 1, right? So that this line, what it's saying is just, if you have 3 neighbors, pick your variable, get the variable of that cell and change it to 1. So 1, it's being alive, so basically this is the born rule, right? A cell gets born once you have exactly 3 neighbors, right? But there's several rules in which that happen if you are alive, right? Let's say that actually kill the cell. So let's copy this line, because this is kind of the template for all the other rules. So there's another rule that says if you're alive and you have less than 2 neighbors, so if you are alive, that's what we're saying in this if statement, and you have less than, smaller than 2 neighbors, so 0, 1, or that's it, you basically die. So you die out of starvation. You don't have enough neighbors to sustain, right? So that's the first one. And right, so the second one would be if you have either 2, so if you had exactly 2, or, that's the way we write an or, you have 3, right? So either 2 or 3 neighbors. I mean, this rule you don't really need to write it, but like if it's saying if you have 2 or 3 neighbors, just stay the way you are, right? You don't die or you just basically stay, right? That's the second rule. As I said, if you are already 1, you don't need to re-specify this, but like I guess it's good to write it down to be explicit. And if you have beyond, you are overpopulated, so you have more than 3 neighbors, right? If you have more than 3 neighbors, your type is going to be 0 again, right? So these are the 4 rules. Just look at them online and you'll find them. You'll see what makes this system work like this. And we're going to try to run it. I'm sure it's not going to work so far. Let's see if we have any kind of script errors. Right, so we're getting something going on, but this doesn't look at all like the game of life, really. It's still interesting, but let's understand what's going wrong. And I said this also in some of the processing tutorials that I have. The problem here is that we are kind of distorting the calculation as we go. Let's say we're going through the loop, and we're changing the first cell in the loop, and that will affect the calculation of the second one, right? So we don't really want to do that, just because that's not the game of life, the way it works. I mean, we want to calculate all the states or the future states of every cell, and then basically once they're done, switch to the real state, right? So how do we do that? We're going to create actually a new variable here in the cube. So this is the script from the cube itself, the prefab. So variable, we're going to call it future state or future type. It's going to be also an integer equals 0, right? So I'm going to save that, and basically in my CA calculation I'm going to change all the rules that actually change the type. I'm going to not change the type, but I'm going to change the future type. So these 4, what they're doing basically right now is just not changing the type itself. So you run through the calculation and then you change the future type, right? So now we basically, nothing should be happening, right? But we could do something else, which is here in the cube, come in the update and say here type equals future type. Just because we do all that calculation for all cubes, and then the cube itself redefines its type based on the future type. So that should make it so you see that really looks like the game of life. Just because we were able to calculate the whole state of the grid based on their actual state, and with that we define the future state. Then after that, as a secondary step, we just switch each cube to its future state, and that happens every frame, so that that's the way you should start getting these kind of emergent patterns. Of course, you can read more about the theory of it in online, and there's several articles from Stephen Wolfram that can help you with understanding how to do this. But this is really useful for all sorts of board games or kind of neighborhood calculations, in which you're just basically asking the cell to the right, are you with a state or with a condition in which you want to evaluate, right? So lots of games really use a system like this one, so it might come pretty handy. We're gonna do probably one more video, so let's go into our grid and maybe just play a little bit with the, don't go too crazy on the size, because you'll definitely crash your computer or get serious problems of frame rate. But you can actually see here how the CA is working. That's pretty cool. I mean, you can go much higher, especially if you do a trick, something like let's see how to, maybe here we could say render dot so if we add this line of code, we could actually turn off the rendering and turn it on in the case. So instead of black and white, we will only have only the cells that we're actually working with, right? So that looks much less. And then again, you can just maybe, in that case where you have less cubes on screen, you can actually go a bit higher in the amount. If you want to see the pattern. So yeah, that's it for this one. We're gonna do one more, I think. I mean, I thought it would be just 3, but I want to just maybe dedicate a little session only to that. And it's a simple way of determining some cube or some other element that could actually affect the cell. So we could just do some collision object that would just navigate here, and maybe it's just creating cells as it goes around. That could produce something quite interesting, and also could help us really work with different patterns emerging out of the activity of other objects, right? So for now, this is it. I'll see you guys soon.